Hi there, welcome back. Today we're going to have just a kind of quick recitation section that reviews some basic properties of the Laplace and Z transforms. Okay, so just in short, what we're going to do, we're going to start off just by motivating these transforms. I did this a little bit at the end of the previous lecture, but I'll just kind of review what I said there. After that, we're going to talk about some very basic facts from the theory of complex variables, okay, which will be kind of useful for us when we talk about Laplace and Z transforms. And finally, where we'll spend, kind of the bulk of our time today, we'll actually talk about these transforms, okay? All right, so let's get started with point 1, which is motivating these transforms. And again, I already talked about this a little bit at the end of last lecture. Okay, so what's the point of doing Laplace and Z transforms, right? Why isn't what we already have good enough? Let's kind of review what we currently have in our study of I/O systems, right? So currently what we have is that we have the I/O relationship y of t equals h convolved with u at t in continuous time, and y at time step k equals h convolved with u at k in discrete time. Right, where here h is the LTI impulse response map and y represents the zero state response of the system, right? So these are nice formulas, but the convolutions involve infinite sums / integrals, okay? And these are still fairly difficult objects to work with, right? They're not exactly transparent, okay? So what we'd like to do now is we'd like to transform all of our system objects in a way such that this I/O relationship becomes super simple to interpret, right? We have a couple of main goals, okay? So goals. If we were to kind of lay out our ideal world for what I/O analysis should look like, maybe we'll have these couple things, right? So first up, maybe we want to kind of simplify the actual dynamics of our system under this transformation, right? So goal 1 will be that the state equations of our system become algebraic. Right? We take what's usually an ODE or a recurrence relation, and under these kind of magic transformations, these things just become regular algebraic equations, right? Maybe that would be useful for our I/O analysis. Now, what's the second goal? Well, the second goal is, up here we said we calculate the input-output relationship via these convolutions, right, which are somewhat complicated objects. So maybe what we'd like is that our convolutions become really simple to compute, okay? So convolutions become simple, okay? We want these to be really nice and easy operations because we're going to be using them all the time for I/O analysis, right? Now third, again, this is kind of looking more towards the future of the course, but I'll say it now. So what else do we want? We want the long-term behavior to be simple to understand, okay? We want to just be able to look at these transformed objects and with very minimal work, be able to tell what this system is going to be doing, as time gets large, okay? And kind of along those lines as well, we want simple interpretations. Okay, so basically almost from inspection, we should be able to tell what our system's going to act like. Okay, so the main insight that kind of lets these things happen is that by transforming our system objects into the complex domain, we can actually realize these goals. Okay, so with a very particular transform under which convolution will become multiplication, all these other properties will kind of fall out as well. Okay, nice. All right, so what we've just said is, if we somehow kind of take our system objects and we transform them into objects in the complex domain, right, in C, then these things will become kind of easier to reason about. All right. So as a kind of result of that, right, it kind of makes sense that we might want to review some facts about complex variables and complex functions before we actually jump into this transform theory. Okay? So that's what we're going to do next. So we're going to talk about some very basic complex analysis. All right? And what complex analysis is it's essentially just the the study of the complex numbers and the functions that kind of act on the complex numbers. Okay? So we're basically just doing analysis, same old analysis, just in the complex plane. All right, so let's go ahead and start with some basic notation. Again, I'm going to keep things at a very high level here, right? I just kind of want you to know the different terminologies and kind of what they basically mean if you ever run across them. Okay, so first up, basic notation. So we'll typically refer to a complex number either with the variable s, which belongs to C, where C represents the complex plane, or z, which belongs to C. All right? So there's a nice fact, which is every complex number admits decomposition into a real and an imaginary part. Okay? So if we take s and c, then we could split s up as the real part of s plus j times the imaginary part of s, where j equals the square root of minus 1. Okay? So note that here I'm going to stick with using the letter j instead of the letter I for the square root of minus 1. This is a convention that mainly comes from electrical engineering, where I is commonly used for current. So I'll just use j here. Okay? Feel free to use I if you feel more comfortable doing that. Okay, nice. So there's one quick point that I want to make about these. Even though we say the real part and the imaginary part, these are both real numbers. Okay? This j takes care of the complex stuff for us. So these are both real numbers. Okay, nice. So we could decompose every complex number into a real part and an imaginary part. What else can we do? Well, we can also take a magnitude of a complex number. So we can take a magnitude. Okay, represents the size of a complex number. Okay, so the complex magnitude is a map, which looks like the absolute value, and it goes from the complex numbers into the real numbers, and it's defined, the magnitude of s is equal to square root of the real part of s squared plus the imaginary part of s squared. Okay, so it looks very similar to the standard Euclidean norm, right? Okay, very cool. So the nice fact about the complex magnitude is that under the complex magnitude, the complex numbers actually become a normed vector space. Okay? So C with this as its norm is a normed vector space over the field C. Okay? And the consequence of this is that all of our standard definitions in a normed vector space, right? For example, sequences, right? Convergence, continuity, etc. all hold in C with the complex magnitude. Okay? So it makes sense to discuss things like the continuity of a function defined from C to C. All right? Okay, so now that we've kind of sketched out these basic ideas, let's talk about some important complex functions. Right? So one of the most important functions is the complex exponential. Exponential. And this is a map, exp, which takes in a complex number and returns another complex number. And it's defined for any s and c. The exponential of s, or e to the s, is written via the real and the imaginary parts. Okay? So this is equal to e to the real part of s times e to the j times the imaginary part of s. Okay? So based on Euler's formula, this is described as follows. So we have e to the real part of s times the cosine of the imaginary part of s plus j times the sine of the imaginary part of s. Okay, so I just want to point out real quick, these are all the real valued sine, cosine, and exponential functions, right? And this is totally perfectly defined because, both the imaginary part and the real part are real numbers, right? So it makes sense to plug them into real functions that we already understand. Okay, so this is a really important function in the complex numbers, right? Not just because it's an exponent and we like exponents, but it also gives us another way to write a complex number, okay? So there's a nice property, says that the exponent gives us another way to write a complex number. Okay? And this is sometimes referred to as the polar form of a complex number. We'll kind of see the reason for this in a moment. Okay? So if I take a variable s and c, then I should be able to write it as s equals r times e to the j times theta, okay? Where r is greater than or equal to 0, and theta belongs to the set 0, 2 pi, all right? So it's more if s is non-zero, this decomposition is unique, okay? And of course, this is taken with theta mod 2 pi, right? So it's unique for theta between 0 and 2 pi. All right, so let's kind of geometrically interpret what this is saying, and once I sketch out this picture, you'll kind of see the reason for the names r and theta, right? So if we're to plot out the complex plane, right, where we have the real part and the imaginary part over here, then what we have is a complex number, s, can be represented as a vector of length r with angle theta from the real axis. All right, so this is effectively what this polar form is saying. We can kind of imagine having polar coordinates for all of our non-zero complex numbers. Okay, fantastic. So we've kind of given a very basic idea of what it means to have a complex number and complex function, magnitude, and the like. Now let's try to kind of set up a little bit of calculus in the complex plane. All right, so what I'm going to talk about in particular is how we discuss differentiation in the complex plane, okay? All right, so let's talk about derivatives. Derivatives in C. Okay, so what I'll say is let omega subset of C be an open set, right, where the definition of an open set is the same as in a normed vector space, right, because C is a normed vector space with a complex magnitude. So let omega be an open set, and f from omega into C be a complex function. Okay, so f is said to be differentiable at some fixed point, s naught in omega, if the following limit exists. So limit as s approaches s naught of f of s minus f of s naught over s minus s naught exists. Okay? So if this limit exists, what do we call it? We call it the derivative, right? So if this limit exists, we call it the derivative of f at s naught, which we denote f prime of s naught. Okay? So there's a couple things that I want to point out. First of them is that this has the same structure as the derivative in r, right? This is really an identical definition. The only difference is here, instead of taking this limit in the real numbers, we're taking the limit in the complex numbers, okay? So the limit is now taken in C instead of R. Okay, so it turns out that complex differentiable functions, because this limit is taken in C, actually have a lot of stronger properties compared to real differentiable functions, okay? So kind of because of this, we introduce some special names to talk about what it means for a complex function to be differentiable, all right? So let me just go ahead and set out this vocabulary, and then we'll discuss it a little bit more. Okay, so what we do is we call a complex differentiable function an analytic function, right? So definition, analytic function. Okay, so I'll say let omega be an open subset of C. A function f, which goes from omega into C, is analytic at S naught in C if it is differentiable in some ball around S naught. Okay? So if I could find a ball like B epsilon of S naught in which my function f is differentiable, right, in which its derivative exists, then I declare the function to be analytic at that point S naught. Okay. So if f is analytic at all S naught in omega, it is said to be analytic in omega. Okay, fantastic. All right, so I want to make a couple of quick remarks about this definition. So remarks, a lot of the times you'll hear the word holomorphic used, okay? Holomorphic used instead of this definition of analytic. For single variable complex functions, these things are identical, okay? Right, there's really no distinction between them. So sometimes holomorphic is used for complex differentiable, and analytic is used for a convergent power series in a radius of the point. But it turns out for f from C to C, these two things are exactly equivalent, okay? This is a really strong property, all right? This is not something that's true at all for real valued functions, right? If I go ahead and I give you a function from R to R that's differentiable, it's not even guaranteed to be infinitely differentiable, right? It might only be once differentiable. Here, we're saying that a function that is once differentiable is infinitely differentiable and has a convergent power series, okay? So this is super strong, right? So it's a very nice property. Okay, and this kind of hints at the fact that if we start working in the complex numbers, we might actually get access to a lot of more powerful properties that aren't true had we just, stuck to working in the real numbers. Okay? So this is kind of nice. All right, very cool. So kind of as a consequence of this definition of the derivative being really identical to what we have in R, obviously minus this limit being different, right? What we have is that a lot of similar properties hold, okay? So basically, if you're given a complex function, you can really just differentiate it like it's a real function, right? All of the same rules are going to apply. All right, let me quickly just state this as a theorem, and I'll just state this informally, okay? So one, what we have is linearity, right? The derivative is linear. So if I take f plus g, both of which are differentiable, and I differentiate them, I should get the sum of the derivatives, right? What else do I have? Well, I have the product rule, right? And that says if I take two differentiable functions, f and g, and I take their product, and I take the derivative, what I get is f prime times g plus f times g prime, okay? And then finally, what I have is the chain rule, okay? So if now I have h of f, and I take its derivative, I'm just going to assume that all of the domains of this are such that all these quantities are well defined, okay? H of f, and I take its derivative at s, what I'll get is h prime f of s times f prime of s, okay? So these are all of our familiar derivative properties from the real numbers, and they all carry through to the complex case. Okay, very cool. All right, so now that we've kind of reviewed some very, very basic terminology in complex analysis, let's go ahead and take a look at the Laplace transform, all right? So next up, what we have is the Laplace transform. Okay, very cool. So here's the basic idea. The Laplace transform is a transform on continuous time signals, okay? So it takes in a continuous time signal and it integrates it against a complex valued function, okay? integrates it against a complex function to produce a complex function. Okay, where this new complex function is called the transform. All right, so basically what we do is we take the product of our original continuous time signal with the complex function, we integrate over all time, all right, and now what we get back, since we've integrated out time, is a purely complex function. All right, so let me go ahead and state the definition of the Laplace transform, and then we'll take a little bit more time to discuss some kind of different interesting points of the definition afterwards. Okay, so let me go ahead and write this out. So definition, Laplace transform. All right, now what I'm going to talk about here is just the one-sided Laplace transform. All right, I'll discuss this a little bit more in a moment. Okay, so I'll say consider a piecewise continuous matrix valued function, which I'll say f belongs to PC of R, Rn by m. So I'll say the one-sided Laplace transform of f is a complex valued function, which I'll call f hat. This maps from omega, which is a subset of c, into Cn by m. And this function f hat is defined f hat of s equals L of f of s, where L denotes Laplace, okay? And this is defined as the limit as epsilon approaches 0 from the left, integral from epsilon up until infinity of e to the minus st f of t dt. All right, this is more commonly just written 0 to the left to infinity, e to the minus st f of t dt. All right, where here this set omega in the definition is defined as the values of s in c such that the integral converges absolutely. Okay, so this is called the region of absolute convergence. All right, sometimes I'll just call this ROC for short, for region of convergence. I'll just assume that it's absolute. Okay, so let's kind of break down the different parts of this definition over here. So there's a few things that I want to say about this. Let's go ahead and highlight remarks. And the first point that I want to make is once we perform this transform, right, there's no presence of t left, right? The variable t has entirely disappeared, okay? So f hat is entirely a function of s. And that's because we integrated t out, right? We took t from 0 from the left up until infinity, and we integrated t over that whole region, right? So there should be no presence of t left in our new function. Now, second, what I said is that here we're taking the integral of a matrix-valued function, right? So, in case you haven't seen this before, all that means is we're just taking the integrals entry-wise of that matrix, okay? So, remark, Laplace transform is defined entry-wise. Okay, so if I give you a matrix, which is a matrix-valued function, f of t equals f11 of t, f22, f12 of t, and so on, right? Then I take L of f and I evaluate it at s. This is the same thing as just doing L of f11 s, L of f12 of s, and so on. Okay? So Laplace transforms are evaluated entry-wise, all right? Maybe you've only seen it in the scalar case before. Okay, now what else do we have? Well, remark 3 is we typically denote the transform with an uppercase letter with a hat. Okay? So I take f of t, and under L, that becomes f hat of s. All right? So, this hat isn't used by everyone, all right? If you feel fine not using it, you can go ahead and do that. But the reason I'm including it is just that, sometimes we'll take the transform of a time domain signal, which is already specified by a capital letter, right? And this just kind of helps us reinforce the fact that we are, in fact, talking about the transform and not the original time function. Okay, what else do we have that we kind of need to, tie up here? Well, for what we had is this limit from the left, right? We started our integral at 0 from the left, which goes to infinity, right? And remember, this is just the same thing as epsilon infinity, limit as epsilon approaches 0 from the left. Okay? So the reason that we do this is to pick up on the Dirac delta function, right? So this picks up on delta, all right? So the basic idea is if we were to do this a little bit more rigorously and say that, we're taking the Laplace transform of the delta, what we would do is we would take an approximation to the identity of delta, which might be defined on all of R, and then we would take the limit as that approximation kind of converges to the true delta. Okay? So this is required to interact well with approximations to delta defined on all of R. Okay? So if we didn't have this, then we would kind of lose a bit of information in our approximation to delta. All right? So if you're interested in hearing more about this, there's an optional section in the notes on how these approximations to the identity are constructed. Okay? So just remember the 0 minus, all that it's doing is it's just there to pick up on the case of the Dirac delta. Okay, fantastic. All right, so these are our main couple points, just to kind of tie things up in this definition over here, right? We have now a function f hat, which is entirely a function of s. We take its Laplace transform by taking these little scalar Laplace transforms entry-wise. We denote it with this, capital F hat, and we take this limit from the left in order to pick up on the delta. Okay, so let me introduce a little bit more terminology. So if I have a signal f, which I'll write out as f of t, then I transform it under the Laplace transform to f hat of s, what I say is that I'm going from the time domain, right, so-called because we have the presence of t over here, and I go into the frequency domain. So frequency domain. All right? Now here, t is referred to as the time variable, and s is referred to as the frequency variable. Okay, so if you're looking for some basic justification as to why this is, well, in the definition of the Laplace transform, we had this e to the minus st, right? Which is a complex exponential. All right? Now, if you remember back to our kind of like basic outline of complex analysis, what we had said is that this complex exponential actually involves sines and cosines, right? And those sines and cosines are kind of determined by the imaginary part of s, all right? So s determines the frequencies of sines and cosines, okay? And because of this, we refer to s as a frequency variable. All right. Now, this is not the only connection between s and frequency. We'll see some more as we kind of go further into the course, especially when we talk about frequency response. But if you're looking for some sort of immediate justification, this is a nice place to start. Okay, very cool. Okay, so above in this definition of the Laplace transform, right, we set out this set omega, right, which is the region of absolute convergence, or ROC for short, right? Because based on the definition, right, which I'll just rewrite out here, e to the minus st times f of t dt, 0 minus until infinity, right? This kind of tells us that this integral is not guaranteed to converge for all values of s, right? For example, if I take f that grows faster than e to the minus st, right, this integral is going to blow up, right? So how can I guarantee that I'm going to have some non-empty region of absolute convergence? Well, we actually need to specify a nice class of signals for which this will happen, all right? Maybe a reasonable idea, reasonable class, is the set of signals bounded by some exponential. Okay, so if I can bound f's growth by some exponential, right, then I should be able to get that this integral will converge, right? Because I have an e to the minus st, so I can control the growth of this other exponential by picking s correctly. All right, so this brings me to the following class of signals. So definition, this is going to be a function of exponential order. So I'll say a function or a signal f, which is piecewise continuous on r greater than or equal to 0 into some space of matrices Rn by n, is of exponential order alpha if there exists an m greater than or equal to 0 such that the norm of f t is less than or equal to me to the alpha t, right? This holds for all t greater than or equal to 0. Okay, so if I'm able to bound the norm of f by some constant times an exponential of alpha times t, then f is said to be of exponential order alpha. All right, and just as a quick side note, since we're working in a finite dimensional space, right, Rn by m, the choice of norm doesn't matter. Okay, this is just due to norm equivalence on Rn by m. Okay, fantastic. So let's kind of see more formally how these things interact with the Laplace transform, right? Let's actually confirm that these signals give us a non-empty region of convergence. So let me state a proposition, which is the transform of a signal of exponential order. Okay, so what I'll say is let f in PC r greater than or equal to 0 Rn by m be of exponential order alpha. Okay, then the region of convergence contains the set of s and c such that the real part of s is going to be greater than alpha. All right, so this set is contained within the region of convergence. If you want to just kind of sketch out what this set looks like, right, let's say that's alpha over there. So the region of convergence will at least be that, right, where the real part is greater than alpha, right, where this guy represents the real part of s and this guy represents the imaginary part of s. Okay, so let me just provide you with a quick sketch of this proof. So proof sketch. If I take the transform of this function f and I just kind of take the norm of what's on the inside, 0 minus to infinity norm f of t e to the minus st dt will be less than or equal to some constant m, 0 to the left to infinity, e to the minus real part of s times t, e to the alpha t, where that bound comes from the exponential order, right, dt, integral 0 minus to infinity of e. Now I'll just combine these exponential terms, alpha minus the real part of s times t dt. And essentially, if this term in here is negative, this integral will converge, right? So what I have is alpha minus real part of s less than 0, which is the same thing as alpha less than real of s, which is exactly this condition up here. Okay, so this set should be contained within the region of absolute convergence. Okay, so just to give you an idea of what a non-example would be, right? So a function that does not satisfy this. If you take the function e to the t, right? And that's going to be quicker than exponential growth. So this is a function that wouldn't have a valid Laplace transform, right? Because we can't bound its growth by an exponential, and we therefore won't get a convergent integral. Okay, so now that we've kind of laid out this nice signal class, we can talk about the transforms of a couple of basic signals. All right. So there's a couple of signals that you should kind of, I don't know, commit the transforms of to memory. All right, like some nice ones that kind of show up a lot. All right. So let me just kind of lay this out. So signal name, definition, transform, and the region of convergence. Okay, so one is the Dirac delta, right, which is, again, not really a signal, as we discussed last time. It's truly a distribution. We could still define its transform. Right? So this is delta of t. Its transform is actually just equal to 1, which is super nice, right? And this holds across all of C. Now, what else do we have? Well, another common signal is the unit step. Right? I'll denote this with this double stroke 1 of t. This is equal to 1 when t is greater than or equal to 0, and 0 otherwise, right? This transform is equal to 1 over s, and that's defined for the real part of s greater than 0, okay? Now, what else do we have? Well, we have the exponential, right, which is e to the at. And this is the transform 1 over s minus a for the real part of s being greater than a, if a is a real number. And finally, we have the sine function, right, which is sine of omega t, where omega is real. And this guy is equal to omega over s squared plus omega squared, right? This holds for the real part of s greater than 0. Okay, so these are some nice common signals. Just try to commit to memory, okay? Commit to memory, right? Once you see these things enough, you'll kind of get a feel for what they are. All right, so let me just quickly sketch out the transforms of a couple of these. So we'll just start with the delta function, because that's a little bit of an unusual one, right? So example, the Dirac delta. All right, and I'm going to be a little bit informal in my derivation of this. You can make this more formal using approximations to the identity. All right, so I just want to remind you real quick of our very informal rule from last time, where we said this integral f of t minus tau, delta of tau, d tau, equals f at time t, right? So this was one of these informal integral rules for manipulating delta as if it were a function of time. All right, so if we go ahead and we apply this to the case of the Laplace transform, right, where now we're interested in computing the integral from 0 minus to infinity of e to the minus s tau, delta of tau, d tau, right? This guy is equal to 0 minus to infinity e to the s times 0. Let me make this a little bit more clear. Minus s times tau, delta of tau, d tau. Based on this rule up here and the fact that delta really collects all of its mass right at the origin, okay, what we have is that this guy is just going to equal e to the 0, okay, which equals 1. And this holds for all s, all right? So this has an arbitrarily large region of convergence. Okay, so just to sketch out a more conventional one, if we take the unit step, right? So this is the function that's equal to 1 for all t greater than or equal to 0. So in this case, its transform will just equal to the integral from 0 to infinity of e to the minus s tau d tau, right? Because the function is just 1. All right. So if we calculate this out, so equal minus 1 over s, e to the minus s times t, where t goes from 0 up until infinity. If we go ahead and we calculate this out, what we'll find is that this thing converges to 1 over s, provided that the real part of s is greater than 0. Okay? And the other transforms follow just via integral calculations. Okay, there's really no special tricks. You just got to grind out a bunch of integrals. Okay, so these examples highlight something kind of interesting, right? So if we take a look at the unit step, for instance, right, which has transform 1 over s, is only defined for region of convergence, real part of s greater than 0. What do we see? Well, here's an interesting idea. So here's an idea. So the region of convergence seems too small, right, for what the functions are. right? So if we take the transform of the unit step, right, which I'll denote 1 hat of s equals 1 over s on region of convergence, real part of s greater than 0. What's the problem here? Well, we know that this function 1 over s can be defined on a much larger region than real part of s greater than 0, right? So we should be able to define this to define on all of c minus the origin, right? Because, we know the function 1 over s makes sense there, right? So why are we stuck with just dealing with this function on the real part of s being greater than 0? Can we actually extend the domain of this function in some nice canonical way? Well, it turns out there's a nice way to do this using something called analytic continuation. Okay? And this is something that I want to point out kind of shows up implicitly in a lot of engineering treatments of the Laplace transform. Okay? So a lot of times what you'll find is that, if you crack open like your undergrad engineering book, you read about Laplace transforms, right in the beginning when they state the definition of the transform, right, they state its region of convergence. And, they're like, this is an important place, this is where our transform converges. But right after they do that, they'll immediately drop it, right? And you'll never hear about the region of convergence again, okay? So it turns out analytic continuation is kind of the rigorous reason why you can be a little bit more loose about this region of convergence, right? It gives us kind of a nice, more precise way of saying, okay, we could really talk about these things on a larger domain. So let me sketch out the idea of what this is. All right. So I'll state a theorem regarding analytic continuation. What this says is consider two complex functions, right? Where I'll take f going from omega to c and g from some set omega prime to c, where omega subset of omega prime subset of c, right? And I'll just assume all of these are non-empty. So let's say f is analytic, okay? Analytic on omega, and g is analytic on omega prime, and the two functions agree on the smaller set omega, right? So, and f of s equals g of s for all s in omega. Then g is the unique analytic function on the set omega prime, such that f is equal to g restricted to omega. Okay? So it's the only analytic function, the only possible function which agrees with f on omega and is still analytic on this bigger set omega prime. All right? So in this case, g is called the analytic continuation, okay? Which I'll just abbreviate CONT of f. All right? So the basic idea of this result is that there's only one way to extend an analytic function to an analytic function on a larger domain. All right, so if we go back to our example of 1 over s, which we said is just defined on the real part of s greater than 0, this is analytic, right? This is complex differentiable, right? And then we take 1 over s, defined on all of c minus the origin. This is still analytic. And obviously, right, it agrees on this smaller domain with this function up here. What this tells us is that 1 over s extended to all of c minus the origin is the unique analytic continuation of 1 over s on real of s greater than 0. Okay? So it's the only possible function which is still analytic and agrees with 1 over s on a real part of s greater than 0. All right? So what this does is this lets us unambiguously extend domains of many transforms. Okay? So if we can identify an analytic continuation, which is pretty easy to do for quite a large class of transforms, then we can automatically just identify our transform defined on maybe this small region of convergence with its analytic continuation to this larger region. All right? And the reason that this is unambiguous is that this continuation is unique, right? There's only one possible choice, so we're not at risk of having to pick between a bunch of different signals and having things be ambiguous. Okay, so this gives us a nice way of, saying, okay, maybe this region of convergence isn't super important. Okay? All right, fantastic. So let's get back and, kind of figure out what a couple of basic properties of this Laplace transform is. And there's really three majorly important properties that I want to state. Okay? So theorem, again, I'll just state this a little informally, just for the sake of time. This is key properties of the Laplace transform. Okay, so these are three of what I think are probably the most important properties. All right, so the first one is that it gives us an analytic function. All right, so analyticity. Okay, and what this says is that L of f of s is analytic on its region of convergence. Okay, so this effectively confirms that analytic continuation is something we can employ. All right, so second property is linearity. All right, so this just says that, because a Laplace transform is defined via an integral, it's going to be a linear transform, right? So if I take L of alpha f plus beta g and s, then what I get is alpha L of f of s plus beta L of g of s, okay? And finally, this is the really important one, right? Remember, one of our original goals was to say these transforms should simplify convolution, right? Because convolution is really what we care about for I/O analysis. So our third property, convolution. And what this says is that L of f convolved with g evaluated at s is actually equal to the product of the transforms, right? So L of f of s multiplied by L of g of s, okay? And this is super important, right? This is probably the most important one. This is effectively what makes this so useful for I/O analysis, right? It says that this ordinarily complicated property of convolution becomes as easy as multiplying two functions together, all right? This is really what makes the Laplace transform appealing to us. Okay, fantastic. So these are what I think probably the three most important properties of the transform are. Now there's a couple others that you should also be aware of that are also really useful for systems analysis. Okay, so let's talk about other important properties. I'm just going to summarize these real quick. Okay, so I'll say the operation, signal, and the transform. So the first operation that kind of shows up a lot in continuous time analysis is differentiation, right? If you take the time derivative of a signal. So if you take the derivative, and the signal that you're taking the transform of is the derivative of f, right? F prime of t. Well, the transform can actually be computed in terms of the transform of f, okay? So this is actually equal to s times f hat of s minus f limit as you approach 0 from the left, okay? So the transform of the derivative is actually kind of computable in terms of the transform of your original function, all right? So this is the first really nice property. So that gives us something about derivatives. Now what we also have is something about integration, okay? So if now the signal that we're interested in is the integral f of tau d tau, right? Starting at 0 and going up until time t, then the transform of this is actually equal to 1 over s times f hat of s, Okay, so if differentiation involves a multiplication by s, it kind of makes sense that integration involves division by s, right? Because these two things are kind of opposites to each other. All right. Now, one final operation that we like is the delay, right? If I delay a signal by time tau. So if I compute the transform of f of t minus tau, then I'll get e to the minus s tau times f hat of s. Okay? So delaying a signal by time tau in the time delay is equivalent to multiplication by e to the minus s tau in the frequency domain. All right? So these are really nice properties. And these things also kind of make it easy for us to compute the transforms of various other more complicated signals, right? So if I wanted to take the integral of one of these simple signals that I outlined over here, I have a nice way of doing that, right? So if I take the integral of the unit step, then right away I would see I get 1 over s squared, okay? All right, fantastic. Okay, so now that we've kind of sketched out the very basic ideas of the Laplace transform, let's take a shot at actually applying this to I/O analysis, okay? This takes us into a discussion of transfer functions. Transfer functions. Okay, so what we had just stated above, right, is that y of t is equal to h convolved with u of t, right? If y represents the zero-state response, h represents the impulse response map, and u represents some admissible input signal. So if I go ahead and I take the Laplace transform of these, using this convolution to multiplication property, what I would get is y hat of s, which is the transform of y, is equal to h hat of s, which is the transform of my impulse response map, multiplied by u hat of s, okay? And this is super simple. All right? Because now all that I need to kind of compute the effect of this input on my system is just a product with this impulse response map transform, right? So this is much, much easier than computing a convolution in the time domain, right? Here we just have a simple product and we can immediately understand what's going on in the frequency domain. Okay, so what's happening here is that the transform of my impulse response map h, it takes us directly from u hat to y hat, right? So it transfers us directly from the transform of our input to the transform of our zero-state response, okay? So because this function over here is kind of so fundamental to I/O analysis, we actually give it a special name, all right? And that name is the transfer function of the system. Okay, so definition, which is the transfer function. All right, so I'll say consider a continuous time LTI system with impulse response map h, okay? So the transfer function of the system is the map h hat, which goes from omega, which is a subset of c, into c p by m. And this guy is defined just as the Laplace transform of h, okay? So h hat in s is equal to L at h at s, okay? It's defined this way for all s in omega, where omega is the region of convergence of the transform. Okay, so the transfer function of the system is simply defined as the Laplace transform of the impulse response map. Okay, so what we'd like to do now is actually compute this, transfer function, right? Because this seems to be a pretty important quantity for us to know. Okay, so now we want to compute the transfer function. How are we going to do this? Well, there's a couple of different ways we could go about doing this, right? First of all, we have some actual continuous time formula for what this transfer function is, right? Written in terms of the matrix exponential and all this different business. But there's actually a much easier way to derive the transform of this system, right? Going down the matrix exponential route might be a little bit messy, so let's kind of try to avoid that. So the first property that we have is an equivalent characterization of transfer functions, okay? So what we have is that if I give you a map h hat, which goes from some region omega to c p by m, and this map satisfies y hat of s equals h hat of s times u hat of s for all input and zero state response pairs u and y, right? Where u hat and y hat are their transforms, then h hat must be the transfer function of the system. Okay? So if I give you a function that has this property for all, arbitrarily transformable inputs, u hat, and their corresponding outputs, y, then that function needs to be the transfer function of my system, right? And the proof of this is fairly simple, right? So you could just take your inputs, u equal like a delta function, right? Multiply it by ej. You could plug it into your system, and you could say, okay, based off of this property, my actual resulting map h hat actually needs to be the impulse response map. Okay, so you can go ahead and work out the details over here. Shouldn't take you too long to do. Okay, so using this basic characterization as this function which satisfies y equals h times u, we can work out what the transfer function for a continuous time LTI system is. Okay, so I'll say proposition, which is the transfer function of a continuous time LTI system. Okay, so I'll say consider a CT LTI system representation, which remember is specified by a tuple a, b, c, d. Then the transfer function of the system is computed h hat of s is equal to c times si minus a inverse b plus d. And this is for all s in omega, where here we can actually define omega to be the complex numbers minus the set of eigenvalues of a, right? So this is often abbreviated as spec A for spectrum, okay? This just means the set of eigenvalues, all right? So we're defining this as this quantity c times si minus a inverse b plus d, where we're having this transfer function be defined on the domain, which is the complex numbers minus the eigenvalues of your A matrix. Okay, so how are we going to go about proving this? Well, let's just try using this lemma that we just stated up here. Okay? Okay, so if we go ahead and do this, what are we going to do? Let's go ahead and start out with our state equation, right? X naught of t equals a times x of t plus b times u of t. Y of t equals cx of t plus du of t. And remember, what we want to compute is the zero state response, right? The response from zero initial condition. So if I go ahead and take the transform of both sides, right, what I'll get is s times x hat of s, where we're going to have no minus term, right, because our initial condition is 0, so we don't need to subtract off x times 0 from the left. By linearity, this will equal a times x hat of s. Again, by linearity, bu hat of s. This will equal, or excuse me, down here we'll have y hat of s equals c x hat of s plus du hat of s. Remember, what I want to look for is a relationship between u and y, right? Some linear mapping from u hat to y hat. So in order to do this, I want to eliminate this x hat in here, okay? So what we have is for all s belonging to c minus the eigenvalues of a, si minus a is invertible, okay? And this is directly from the definition of an eigenvalue as something that makes the determinant of si minus a equals 0, okay? So if we're not at one of those points, this will be an invertible matrix, right? Otherwise, it would need to be an eigenvalue. Okay, so let's say for such an s, right? If we go ahead and solve for x hat in the top equation, what we'll get is si minus a, x hat of s is equal to b times u hat of s. So x hat of s is equal to si minus a inverse bu hat of s. We go ahead and we plug this into the lower equation. What we'll find is that y hat of s is equal to c si minus a inverse b plus d, all multiplied by u hat of s. Okay, and that gives us our proof. And remember over here this fact that this thing is defined on all of c minus spec a. This thing kind of follows from an analytic continuation argument, right? So if we were to directly compute, the Laplace transform of our impulse response map, maybe it would give us some other domain, right? We could actually go ahead and extend that domain unambiguously to c minus the eigenvalues of a. Okay, fantastic. So what this gives us is a nice way to compute the transfer function of our system, right? So now, I am writing with highlighter. So now what we have is y hat of s equals h hat of s times u hat of s, right? We can compute each of these terms, right? So u hat we should know how to compute for a sufficiently simple signal. H hat we just showed how to compute. So what we're pretty much ready to do is to perform IO analysis using these transform methods, right? What we might like is a way to turn y hat back into a time domain signal. Okay, so this gives us a super easy way to compute y hat as a frequency domain signal, right? No convolutions required, right? Just take a product of two functions. Now what we'd like to do is to go backwards, right? In order to go backwards, we need to invert the Laplace transform, all right? So I'm going to briefly talk about how we do this. So let me state a definition. This is the inverse Laplace transform. Okay, so the basic idea is the following. So the inverse Laplace transform is a map L inverse, okay, just because it's the inverse of L. And what this does is this takes a complex valued function, which I'll call h hat, right? Not necessarily my transfer function, it's just some complex valued function. H hat from omega subset c into Cp by m to a real signal h, which goes from r greater than or equal to 0 into Rp by m. And this needs to satisfy the following, right? So L of h of s is equal to h hat of s. This holds for all s in omega, okay? So my inverse Laplace transform simply takes me from this complex frequency domain signal into a time domain signal, which under the Laplace transform gives me back my original frequency domain signal, okay? All right. So there's a couple of questions that show up whenever you try to take the inverse of something, right? So does the inverse exist? And is it unique? Okay, so both of these are actually pretty hard questions to answer in general, right? There's actually quite a bit of analysis that goes into answering both. I'm just going to give you a very simple answer to both of these questions, okay? So unique, I'll talk about super quickly, okay? I'm not going to dwell on this too much. So unique, at best, you can hope for uniqueness up to equality outside sets of measures 0. Okay, and if you haven't heard of these before, these are effectively sets of numbers that are ignored by integrals. Okay, so these are sets ignored by integrals. Okay, so an example of this would just be a single point set, right? So let me just call this x, or let me give you an example, like 0. All right? So, if the value of a function changes at one single point, the integral will pretty much just ignore the change at that point, right? It won't even notice. So the basic problem is that if you have two functions f equal to g everywhere but on a set of measure 0, they'll have the same Laplace transform. Okay? Because the Laplace transform is defined via integration, right? So the problem is that once we have those transforms, right, and we go to invert the transform, we won't know which function to pick, right, f or g, because they both have the same transform. So this means that really the best we can ask for is uniqueness of the inverse up to equality outside of sets of measure 0, okay? So if two things differ on a set of measure 0, doesn't matter, all right? And this will be a pretty satisfactory answer for us. Okay, so I want to just outline a class of functions, complex functions, which has kind of a unique, well-defined inverse in this sense. All right, so I'll say lemma, and what this is the inverse of strictly proper rational functions. Okay, so I'll say consider a complex function which is the ratio of two polynomials with real coefficients. Okay, so maybe I have some function, let's call it g hat of s, and this is equal to am s to the m plus a1 times s plus a naught, so a polynomial in the numerator. Then I have another polynomial in the denominator. Okay, so maybe I have bn s to the n plus b1 times s plus b naught, where here, right, these are all real coefficients, ai, bi, and r, even though s is a complex number, right, we're taking real coefficients. And just in order to make sure that this thing is well defined, that these polynomials have well-defined degrees, m and n, I'll assume am and bn are non-zero, right? In this way, we can identify m as the degree of the numerator polynomial and n is the degree of the denominator polynomial, okay? So just to kind of say what this is called, is that if m is less than n, this is called a strictly proper rational function. Okay, sometimes you'll hear it called a strictly proper real rational function. It's rational because it's the ratio of two polynomials. Okay, so what happened there? The nice property is that if m is less than n, right? If we have one of these functions, then we get a unique inverse Laplace transform up to equality outside sets of measure 0. Okay, so let me just give you a very quick proof sketch of a kind of simple case of this. And the case that I will kind of give you is that the roots of each polynomial are distinct, okay? So each polynomial doesn't have any repeated roots, and I'll just assume that they're all real as well. Okay, so what this means is that in this case, I would be able to factor this guy out as follows, right? I would be able to write it as, let's see, s minus the first root. Let me call this 1a. And I'll multiply this out, s minus s, ma, where each of these are fixed numbers representing each of the m real roots, right? Denominator, I could do something similar, right? I could have s minus s1b all the way to s minus sn comma b, all right? It turns out via partial fractions expansion, I could rewrite this guy as c1 over s minus s1b plus cn over s minus sn comma b, right? And if you go ahead and you kind of review these basic Laplace transforms that we outlined above, this is the Laplace transform of an exponential, right? So if you take e to the, what would this be in this case? Si comma b times t that'll have a transform equaling one of these expressions over here, right? So that gives you existence of the inverse, all right? Uniqueness I won't discuss here just for the sake of time. Okay, so that's a very basic proof sketch. I've included some references in the notes to where you could find a more complete proof of this. Okay? All right, very nice. So the basic process is, let me just review. What you do is you compute the transform of your output, y hat of s, via h hat of s times u hat of s, right? Because convolution becomes a multiplication. And then you compute your actual zero state response in the time domain via inverse Laplace transform, right? L inverse of h hat of s times u hat of s, okay? And that allows you to go start from finish in this frequency domain. No convolutions required. All right, fantastic. All right, so that pretty much finishes up our discussion of the Laplace transform. Now I'm going to go ahead and quickly discuss the Z transform, all right? So we're going to move a lot quicker here, and the reason for this, which I'll kind of explain in just a moment, is that the Z transform is really a direct discrete translation of the Laplace transform, okay? So much of the theory is pretty much identical. All right, so let's talk about the Z transform. So remember, what we've done so far when going from continuous to discrete is we've performed kind of a series of translations, right? Wherever we see a time in t, right, we replace it with a time step in k, maybe times, I don't know, some sampling interval. And likewise, wherever we see an integral, we replace it with a sum, right? So we're going to do the same thing here to kind of motivate the formula for the Z transform, all right? So remember, your Laplace transform is defined L of f of s equals the integral 0 left to the infinity e to the minus st f of t dt. Okay? So the first thing that we're going to do, right, is we're going to replace the integral with a sum. Okay? That's standard. Now what else do we have to do? Well, we have to replace this with a discrete time signal, f of k. But now I want to talk about what we're going to do about this exponential, right? What's the analog of the exponential in discrete time? Well, if I go ahead and I sketch out what an exponential decay looks like, right? And I go ahead and I sample this at a fixed time step delta, right? Sample, sample, sample. So I'll have delta, right? This will be 2 delta, 3 delta, and so on. Well, what are the values at those different instants, right? So let's say this represents e to the minus st. Now, obviously, I'm plotting a complex function as if it were a real function, but just bear with me for a sec, okay? So what do I do over here? Well, let's say that, I'll define my sampling times tk equals k times delta. So then I have e to the minus s times tk is equal to what? Well, this is equal to e to the minus s times k delta, which is equal to e to the minus s delta. Actually, let me bring this minus out with me to the k, right? So what I can do is that this guy on the inside is just a complex number, right? So I can just remove this exponential and just say I'm going to define this as z to the minus k, right? For z some complex number. Okay, so what we've done is we've taken this exponential, which appears in continuous time, and we've replaced it with a geometric term. Okay, so this is a geometric growth instead of an exponential growth, all right? And this really leads to the definition of the Z transform, okay? So what we're doing is we're replacing an integral with the sum, we're replacing continuous time signals with discrete time signals, and we're replacing an exponential with a geometric term, which is really just a sampled exponential, okay? All right, so this leads us to the definition of the one-sided Z transform. So definition, one-sided Z transform. Okay, so I'll say consider a discrete time signal, which I'll denote f with square brackets. This goes from z greater than or equal to 0 into r by m. So the one-sided Z transform of f is the map on the complex numbers, f hat, which goes from omega into Cn by m, right? And this should kind of feel familiar. And instead of being defined via an integral, this will be defined via sum, right? We'll have f hat of z equals the sum going from k equals 0 up until infinity of z to the minus k times f of k, right? And we denote this as z of f evaluated at z, okay? So this is called the one-sided z transform of f, right? So just take a moment, stare at this formula, kind of convince yourself that all we've done here is replace the integral with a sum, the exponential with a geometric term, and a continuous time signal with a discrete time signal, okay? So just make sure that you kind of understand that comparison. All right, so the nice thing is that the z transform really has all of the same key properties as the Laplace transform because it's defined directly in this translation way, okay? So in particular, the biggest important property that we have is that discrete time convolution is again multiplication, okay? So now if I have two discrete time signals and I take their convolution, what I get is the product of these signals, okay? So z of f of z times z of, g at z. All right, so the same key convolution property holds. That's what makes this thing really important, okay? So one other property, so let me call this, step forward by 1. And this property says that if I have a signal f k plus 1, right, versus my original signal f of k, then the z transform of this signal, z of f k plus 1, evaluated at z, will equal to z times f hat of z minus zf of 0. Okay? So this is essentially the analog of the multiply by s to get a derivative. All right? And as a consequence of this, if you again define the transfer function as now the z transform of your discrete time impulse response, you'll find that h hat of z is computed c times zi minus a inverse b plus d. Okay? It's going to be on the same domain as above. So just a final takeaway. Something that you should look out for. You should really try to draw parallels between the Laplace and z transforms. Okay? If you do this, you can make your life a whole lot easier, right? If you see stepping forward by 1 is kind of the discrete time analog of differentiation, then a lot of proofs that involve stepping ahead by 1 will essentially follow directly the same as the Laplace transform proof. Okay? So if you're interested in learning a little bit more about the z transform, because I know this was a little bit brief, there's a more thorough treatment in the notes. Otherwise, I've posted some more standard references to where you can find more about this material. Okay, thanks for watching.